Hi, this is Dr. Hay. We're going to talk about the electric field due to a continuous distribution of charges. So we defined the electric field due to a system of point charges or source charges as this equation up here. Now I've written in summation form, so I just indicates the number charge, so we could call this Q1, Q2, Q3, etc. It's just for a distribution of point charges, and I goes from 0 to however many charges there are. So let's say you want to know the electric field at this point up here. Each one of these charges contributes an electric field to the entire electric field that makes up that whole field. But let's say you have so many charges now that it really just becomes more convenient to treat this entire system of charges as a continuous distribution of charges, a continuous distribution of charge. In the same way that in mechanics we had continuous distribution of masses, once you had so many small mass particles that it was easier just to think of something as a large rigid object than a bunch of point masses. So we're going to do the same thing here with electric field. We want to find the electric field due to a continuous distribution of charge. Every part of the distribution contributes to the electric field in the same way that each point charge contributes to the electric field here. Instead of adding the electric field for each of the charges, we're going to sum or integrate to find the total electric field. So instead of an equation that looks like this, I'm going to write the other one here so you notice the similarities between them. The electric field for a continuous distribution is going to look like this. Instead of a sum, an integral, and this is the same Coulomb's constant as it is over there. R hat, now you're talking about the direction. In both cases we have an R hat, which indicates the direction of the field. But on this one we have an integral, and so we need an integration variable, dq. So this is our differential dq. Now this is for an entire a distribution of charge where, let's say you've got a little piece of volume here, and this little piece of volume is contributing to the electric field. At this point, you're trying to find E. Here's a little piece of charge. We're going to call this little piece of charge dq, the differential variable. So this little piece here is dq. Now dq can be written much like it was for dm in the mechanics mass problems that we did, as density times volume. Now this density is charge per volume, not mass per volume like it was in mechanics. This is charge per volume. If you have a volume containing dq, then you're going to have this rho density, charge per volume, times a little bit of volume. If instead you have area, so this is for volume, if instead you're trying to find the electric field due to something with surface area and not volume, let's say you're doing a flat plate or a disc, then your dq is going to look something like sigma d area. In this case, sigma is charge per area times now dA, and that's going to be equal to dq. If, on the other hand, you have a line of charge, then, like you've got a line or a ring, then dq is going to be, let's write, linear. Then dq is going to be lambda. You notice it's very similar to the mass problems that we did before, dl, where this is a length of charge, or this is a length, and here's the charge per line, or charge per length, dq. So notice that the units are consistent all the way throughout here. dv, dA, and dl mean that the integration variables will be spatial, not special, spatial. So the integration variables will contain something like, these usually contain and they will be spatial, not special. And they'll contain things like x or theta or things that can be integrated over in space.